Greetings, and thank you for watching this presentation that is one of the resources included in the Create Energy Center's Solar on Schools Toolkit. The work presented here was originally described in a manuscript entitled Enlightened Education, Solar Engineering Design to Energize School Facilities that was recently published with the American Society for Engineering Education. This work won a Best Paper Award at the ASEE Annual Conference, and we are including it in the Solar on Schools Toolkit so that we might reach a larger number of faculty and schools with an interest in pursuing solar projects at their campuses. This presentation and the ASEE publication examine some of the engineering considerations and lessons learned that went into the design of a new 1.85 megawatt solar photovoltaic system that was commissioned in 2019 by Madison Area Technical College in Madison, Wisconsin. We have also created a virtual field trip tour of this solar installation, and we encourage those that are interested to check out this recording to see video footage of the PV system shot from the college rooftop, along with a more detailed discussion of the technical aspects of the design. The virtual tour and many other resources are included in the Create Energy Center's Solar on Schools Toolkit, which is available for download from the website www.createenergy.org. This is an aerial view of the Madison College solar photovoltaic system. The system contains 5,700 solar PV panels for a total system size of 1,850 kilowatts or 1.85 megawatts DC, making it the largest rooftop solar system in the state of Wisconsin. The system is composed of multiple subarrays that are installed over a dozen different roof sections and elevations that comprise the 1.1 million square foot facility. When skies are clear, the system produces enough electricity to provide 100% of the power needed by the building for several hours in the middle of the day. Of course, many days in Wisconsin are cloudy, and the college also teaches classes at night. So when averaged over the year, the system provides roughly 25% of the energy consumed by the building. This is equivalent to the amount of electricity consumed by about 300 average-sized residential homes. The solar system at the Truex campus was completed as part of the college's solar PV roadmap. The college created the roadmap in 2018 with the assistance of the Midwest Renewable Energy Association to examine the potential for solar energy at all of its campuses and facilities. The roadmap planning team began by identifying the motivating reasons to pursue solar energy, and the top-ranked goals were to provide cost savings to the district and to provide learning opportunities for students. Since the Truex campus is the largest energy consumer in the district, and it also serves the largest number of students, this building was identified as the top priority for the solar roadmap. The college also completed a solar installation at its Goodman South campus in 2019, and solar construction work is currently underway at the Commercial Avenue, Fort Atkinson, and Reedsburg campuses, with projects to be completed yet in 2021. The college's ultimate goal is to execute solar projects on all of its buildings. However, it is not practical to engage in dozens of projects all simultaneously. By creating a solar roadmap, the college was able to strategically prioritize its solar investments. Financial considerations were a strong motivating factor for Madison College to pursue solar power, and we are frequently sought out to share economic information about the project and the value of solar energy. The project was incentivized in part by a cash grant program offered by Madison Gas and Electric that was established through a settlement agreement with the Environmental Protection Agency. The grant provided for about 20% of the system cost, and the college paid for the remaining portion. The solar panels have a 30-year warranty, so this was chosen as the time horizon for the economic analysis. Note that there are many solar panels that have been operating for much longer than this in the field, so this is a conservative estimate. The system has a simple payback period of just under 10 years and an internal rate of return of about 10.5%. The levelized cost of electricity for the system is 3.8 cents per kilowatt hour, which is less than half of the retail rate that the college currently pays. Like most large educational institutions, Madison College has separate budgets for capital and operating expenses. Over the past couple of decades, the college has frequently experienced deficits in its operating budget due to expenses that escalated at rates exceeding those of inflation. An additional financial benefit provided by the solar system is that it allowed for the investment of capital construction dollars to build infrastructure that could provide energy for the school and thereby reduce future operating costs. This sort of cost hedging approach helps to stabilize the college's operations by locking in a portion of the school's future energy costs, making for more controllable and predictable budgeting. Learning opportunities for students was another strong motivating factor for Madison College to pursue solar energy. The college has had a renewable energy certificate program since 2005, and solar energy is a predominant technology featured in the program. The foreman on the solar installation was a Madison College alumnus, and several of the people on the crew were enrolled in the college's electrical apprenticeship program. The solar system was intended to be used as a teaching tool for Madison College students. However, the only previous access to the roof was to climb up a vertical ladder and up through a ship's hatch door. This situation would obviously not be compliant with the Americans with Disabilities Act requirements for instructional space. So, the college built an ADA accessible ramp and cut a hole in an exterior wall to install a new glass exit door opening onto the roof. The space surrounding the ramp and exit door has windows that look out onto a section of the solar system so that it can serve as an observation area for tour groups even if the weather is not favorable for viewing the solar panels up close outside. An interpretive display with photos and factual signage was also installed in this area to inform students and visitors about the system. The glass exit door shown in the previous slide opens onto the lower roof section shown in this photo. This section is designated as an outdoor classroom for students enrolled in the college's solar photovoltaic courses. The panels shown here represent a bit less than 1% of the total system, arranged in two strings of 20 panels each. This array can be electrically disconnected, de-energized, and locked out from the rest of the solar system so that students can then work safely on this section. The panels can be disassembled by staff and then reassembled by students learning safe installation, inspection, and commissioning practices. Because this array is located on a roof section having a lower elevation than the rest of the surrounding building, it is physically impossible to fall off the edge of the roof from this position. This also makes the space suitable for public outreach through tours, open house, and student recruitment events. With the installation of the gray traction walkway treads, the space can safely accommodate groups of over 100 people at a time. The system features multiple types of roof surfaces, such as the black EPDM rubber roof seen on the left, the white TPO polymer membrane roof shown in the center, and the standing seam metal roof shown on the right. Each of these roofs have different thermal characteristics, and students in the college's renewable energy program are able to compare the output to see the effect on electric potential, instantaneous power output, and annual energy production. The system makes use of both south-facing panels, shown in Figure A, and east-west facing panels, shown in Figure B, and students can also compare the performance of these subarrays to see the effect of panel orientation on electrical production and to see if the actual results from the field match theoretical model predictions. The system includes a solar performance dashboard that provides real-time monitoring of system output, as well as archiving of data for the life of the system. This information is also displayed on a flat-screen kiosk located near the rooftop classroom and indoor observation area. This photo shows a week of solar production for March 2020, along with some of the financial and environmental benefits of the system. The system uses solar edge DC to AC inverters and module level power electronics in the form of DC power optimizers. Each optimizer serves a pair of solar modules and has its own communication signal that transmits data to the inverter. The inverter then sends this data to the cloud, where it is archived and can be accessed by students for analysis. Sections of the system can be selected and magnified to see output of individual strings and panels, as shown in the green box for the student instructional array. The following slides show a quick example of the type of student learning made possible by this system. The upper graph on this slide shows the solar output in megawatts on the vertical axis for a week in November 2020, with the date shown on the horizontal axis. The lower graph shows the temperature and humidity on those same dates. A weather event happens on the evening of November 5th, as the humidity peaks at 100% and the temperature drops below 32 Fahrenheit. This represents the first snowfall of the year for the past winter in Madison. Of course, the question we always get is, what happens to the solar output if the panels get covered with snow? This past year, students had the opportunity to do this experiment firsthand and gather data to quantify the effect. The student array was de-energized and locked out, and then students were able to clear and remove snow from the first of the two strings that comprise the instructional system. This slide contains the data that students retrieved and analyzed from the solar system's data acquisition archive. For the first 2 days of the week, the two strings of panels showed in red and blue have essentially equal electrical production. On day 3, when the two strings are both covered in snow, the power output drops to near zero. Then we see that on the last 2 days of the week, the blue string of panels that had the snow removed greatly outperforms the red string of panels where the snow was left in place to weather naturally. Of course, this result is not surprising, but that is also not the point of this lesson. The really interesting question is if it would be cost effective for the school to pay a maintenance person to remove snow from the solar panels. Students actually performed an analysis to answer this question. They determined the amount of time required for removing the snow, accounting for documentation of a work order, retrieval of a shovel and broom, dressing for the outdoors, etc. They then developed estimates for the maintenance person's hourly wage and benefits, and determined the value of the additional electrical energy that could be produced as a result of cleaning the panels. The end result of the analysis was that it was not cost effective to pay for snow removal, and rather the snow should just be left to weather away naturally by the action of sun and wind. Of course, the faculty and staff at the college had already done this analysis, and we knew the answer. But the learning opportunity for students was of great value as they explored this question for themselves and processed real-world data to reach their conclusion. Madison College has created a 10-step guide for other schools that might be interested in pursuing a solar roadmap for their campus. The 10 steps are assembling a team and articulating a purpose, list and rank motivating objectives, identify stakeholders, quantify current energy usage and costs, examine energy management practices, assessing sites for solar, seeking and securing sources of funding, modeling and prioritizing projects, disseminating the plan, and implementing projects. A further description of each of these 10 steps is available in the how-to guide. You can download this document along with an executive summary of the Madison College Solar Roadmap from the Center for Renewable Energy Advanced Technological Education. Please visit www.createenergy.org and go to the publications page. While there, you might want to sign up for the Create mailing list to receive our newsletter and more updates on our work with solar and renewable energy education. If you are interested in learning more, please check out the virtual field trip of Madison College's Rooftop solar system that is part of the ASEE virtual conference. This work was made possible by Madison College, the Midwest Renewable Energy Association, Sunvest Solar, and Madison Gas and Electric. The work was supported in part by grants from the National Science Foundation and the U.S. Department of Energy. Thank you for viewing the presentation, and I hope that you enjoy the rest of the ASEE conference.